Considering again the function r of t equals 3 cosine omega t I plus 5 sine omega t j, which is just a vector representation of the parametric equations we saw in the preceding x of t equals 3 cosine omega t, y of t equals 5 sine omega t. We asked the question, is this a possible orbit with the sun at the center? And we determined that it wasn't so because the r squared d theta dt was not constant. So we don't have that necessary condition. Let's see if there's something we can discover from the velocity and acceleration vectors that would contradict the possibility of an orbit with the sun at the center. That might be simpler than taking all these derivatives was. So our r of t vector at any time t is just going to be a vector from the origin to the position of the object in the orbit. Our dr dt vector is going to be tangent to the orbit, to the path of the orbit. And our r double prime of t vector, in order for this to be a possible orbit with the sun at the center, remember that the net force has to be back toward the sun being the object that's attracting the planet, and that force of attraction acts back toward the sun. The force of attraction on the planet acts back toward the sun. If it turns out that the r double prime of t vector is not in the negative radial direction, in the direction back toward the origin, then we're going to conclude that this couldn't possibly be an orbit because that would imply a net force that's not in the direction of the sun. Well, we can easily calculate r prime and r double prime, and this is a very simple calculation. The derivative of the cosine of omega t is negative omega sine omega t. Derivative of sine omega t is omega cosine omega t. We take a second derivative, and we obtain this result for r double prime. And it's fairly easy to note that if we factor the omega squared out here, what we're left with is just our r vector, so that r double prime equals negative omega squared r of t. And this is radial back toward the origin. And this is no contradiction. Now, does this guarantee that this is a possible orbit? Well, you would suspect that since our previous result showed that it couldn't be, that the answer is no, but it doesn't contradict the idea of a radial force. So what was the other aspect of this force? Well, the other aspect of the force the other condition was that the acceleration be negative g m over r squared times our radial vector, and that's not r, that's u sub r. I'm not going to bother to blot that out. Inverse square condition. We've shown here that r double prime, which is our acceleration vector, is a negative multiple of the radial unit vector. Not contradicting this, but the inverse square condition, the condition that this acceleration be inversely proportional to the square of the distance, that is contradicted. Well, actually we already wrote, yeah, no. Didn't look closely enough at what I'd already written. This is a contradiction. These are the only two conditions. It's radial, it's an inverse square. If these two conditions hold, then this is a possible orbit. But since we know that the necessary condition does not hold, then this force will not be an inverse square. And we could go into the calculations, and we might come back to this later and show that this force does not result in an inverse square. but for now we're going to leave that, and we're simply going to move on to the idea of a unit tangent and a unit normal vector. Simply that here we have the path, here we have the derivative, and if we do a unit vector in the direction of this derivative, that's what we're going to call our unit tangent vector, t of t. If we take the derivative of this unit tangent vector, that's going to give us a vector that's radial back toward the origin. Now this model can be applied to the question we have here, but this model is completely independent of this question. We're just using this example in order to motivate and give us a model in which we can make sense of this idea, and we're going to go on with that in the next clip. Okay, we again have the vector r of t that we've been talking about, and we easily find the derivative of r of t equals negative 3 omega sine of omega t I plus 5 omega times the cosine of omega t j, and r double prime of t equal negative 3 omega squared cosine omega t minus 5 omega squared. Now that's times I 5 sine omega t, 5 omega squared sine omega t times j. So we have our r of t, r prime of t, and r double prime of t vectors. Our unit tangent vector that we defined previously, which is just a vector in the direction of r prime of t, in the direction of our velocity, but it's got to be a unit vector, so that's just r prime of t divided by the magnitude of r prime of t. And what's that equal? Well, we have our negative 3 omega sine of omega ti plus 5 omega cosine of omega t times j divided by the square root of the sum of these squares. That's going to be the square root of 9 omega squared sine squared of omega t plus 25 omega squared cosine squared of omega t. Now, this denominator has a common, well, the square root has a common omega squared. That can be factored out, giving us an omega, and that's going to divide our omegas so that our unit tangent vector is going to become negative 3 sine of omega t I plus 5 cosine of omega t times j divided by this square root. Now, I can take, remember the omega squared has been factored out and divided into this omega. The 9 sine squared can be matched with 9 of the cosine squareds and give us just 9. 9 times the quantity sine squared plus cosine squared of omega t naturally, leaving us 16 of these. So we have 9 plus 16 cosine squared of omega t. It's not necessary to do this simplification, but it's going to make the next step a whole lot easier. And in the next step, we try to find the derivative of that unit tangent vector.